Alright, let's take a look through the boot process of xv6. In order to get xv6 for this assignment, all you have to do is unpack the starter code for homework 9. So you can see I've just unpacked it here with this tar xcvf command, and unpacking it gave us a xv6 directory, which has source code for this complete xv6 operating system. That's not helpful. If we go into the starter code for homework 9, you can see we have the test script for this particular assignment, and we have this directory of the xv6 operating system. In here we have about a screen and a half worth of files, including some files that are marked executable. In order to run this version of xv6, all we need to do is type in this xv6 directory, we have to type make qemu no x. That's assuming you've installed all the prerequisites as described in the assignment. So we type make qemu no x, it will build the system. We're building a complete operating system, we're booting from the hard disk, simulated hard disk, and the result is that we get this $sign prompt where we can type a shell command. So we can type ls, and we'll see the content of the root directory of this simulated disk, the operating system running in this QEMU virtual machine, and we can do stuff like cat readme. That'll print out the contents of the xv6 readme file. Then when we're done, we can type halt, which will shut down the virtual machine and bring us back to our host operating system. All right, so let's go ahead and take a look at how this thing boots up. Our story starts in a file called bootasm.s. So the bootloader has done its job and has loaded up the initial stage of our operating system kernel. Let me zoom in just once. That makes us scroll off the screen a little bit, but it might make things a little bit clearer if you're not watching this on the hugest display. So here's where we start executing, right here on line 10. And the first thing that you'll notice here is this says code 16, because this is 16-bit Intel assembly code. So not AMD 64 code, not traditional 32-bit Intel x86 code, but even more traditional 16-bit code for the Intel 8086 or 8088. We start at this start label, and the first thing that we're going to do is we are going to disable interrupts. Interrupts are pretty important in our story. Interrupts are how the CPU knows that it needs to stop what it's doing because something interesting has happened. Usually what has happened that's interesting is some other piece of hardware has had an event occur, maybe someone pressed a key on a keyboard, and in order to let the CPU know that something has happened and that it needs to go figure out what that was and handle it, we have this interrupt mechanism. For something like a key on a keyboard, it's going to cause an actual signal to go down a physical wire into the CPU on a pin, and that pin will have an interrupt number, and so we'll have interrupt, for example, 12 occur, and then software needs to handle that. But the way it handles that is by running interrupt handling software, and we are just initially booting the operating system, so we don't have any interrupt handlers installed, so we want to turn off interrupts so we have long enough to set up so that we can handle them properly. Next thing that we're going to do is some stuff with segment registers, and this is sort of precursors to how virtual memory works, but the details aren't super important. Then we have to do this trick where we have to undo physical address line 20 being hard set to 0 because there was some initial trouble with sort of post first generation IBM PCs, so like third generation IBM PCs that had more than 1 meg of RAM. And there's a compatibility hack that we still have to deal with. Once we get through that, we eventually are going to switch from real mode to protected mode. So that means we're going to get into a mode where it's possible to enable virtual memory. We won't have fully enabled virtual memory, but we're going to make it possible to do that. And as part of that, we're going to jump from our 16-bit code, which was our initial thing that we were doing, to 32-bit code. And xv6 is targeting Intel 32-bit. If this were a 64-bit operating system, I believe at this stage we would be jumping directly from 16-bit code to 64-bit code. But here's the line of code on line 51 here, where we're doing a long jump, and that's a instruction that mostly we don't have to worry about on modern systems. I guess exactly one of them happens every time we boot our computer, but this allows us to jump further away than in the current segment, and segments would have been limited to 64K, so we're jumping somewhere in memory more than 64K away from where we are. And specifically where we're jumping is the start32 label, which is 32-bit assembly code. Now again, we're going to muck with our registers a little bit. Again, we don't have to worry about it with our segment registers. Again, we don't have to worry too much about how the segment registers are getting set up. The important thing is that we are going to set up our initial stack pointer, and we're setting it to this start label. Interestingly, I think that might be this start label up here. So yeah, this is making line 12 of our assembly code into the top of our stack. So that'll make it so the stack is going to grow down from there, so this way. That's interesting. Apparently we can get away with that. And then the other thing that we're going to do here is we're going to call a function called bootmain. Conveniently for us, bootmain is C, so we get to go look at C code now. But the startup was around 60 lines of assembly. So bootmain appears in a file called bootmain.c, and is this function bootmain. So we're going to call into this function first C code we execute as the kernel boots. Now, we haven't actually started running the main portion of the kernel. We're in this like kernel bootstrapping phase, the like first stage of the kernel. So what we need to do now is load the full kernel from disk. To do that, we're going to set up some structures to deal with reading data off disk. We're going to allocate some memory. The way we allocate memory at this point, we're before even having a kernel memory allocator. So the way we're going to allocate memory for this structure right here is just hard coding this address. We are the kernel. We're allowed to access all of physical memory. The way we set up our segments means that memory addresses are still mapped to physical memory addresses, and accesses to physical memory aren't going to cause seg faults. So we really can just pick an address in memory that we know doesn't have anything important at it, and just start writing there. And that's how we're allocating memory for this structure named elf. Now once we've done that, we're going to read a single page, 4096 bytes, off disk and into this structure. And then we're going to make sure that we have the correct elf magic. And elf magic is very important for getting an operating system kernel to start. More specifically, elf is the file format that we're using to store stuff on disk, and checking this magic field allows us to verify that this thing that we read off disk really is in the appropriate file format, because it specifies a constant that will be on that field to indicate this file type. From there, we're going to load the segments of the program from disk into different locations in memory. So this is things like the text and data segments of the executable that is the main portion of the kernel. And then we're going to call a function called entry. And this function called entry is actually the function that is the main function in this executable that we loaded from disk. So our code continues in a function called main, and we're actually in the primary stage of kernel execution at this point. So we're looking for a function called main, and it's right here. So in this main function, we do a whole bunch of stuff to initialize booting. I'm going to go through it kind of quickly. First thing is we're going to deal with memory allocation. To do that one memory allocation for that elf structure, we hard-coded a memory address, but we don't want to do that forever. So there is a kernel memory allocator, and these two functions are initializing that kernel memory allocator and making it so that it can allocate pages of memory. Sort of the other end of what on a modern Linux system would be mmap. Now this is a operating system that can handle multiple processors. So we're going to go ahead and initialize other processors if they're running and make sure that they're running the right code that they should be. They start somewhere else, but they don't do much, so we're going to ignore them. We're going to handle one of the interrupt controllers. There's at least two of them here. We need to set up the hardware that we need in order to make this operating system work. And this hardware is going to have a text console where we can type commands, and it's going to have a serial port, which we could do serial communication. That probably was important back in 1975, but nowadays you have to go out of your way to get a machine that has a serial port. Although standard serial ports do totally still exist, and you can buy new machines that have standard serial ports on them. We're going to set up some other stuff like the process table. We've talked a little bit about that before. We're going to set up this thing called the trap vector. And that has to do with how we're going to handle interrupts. These things are about the file system. So we're going to set up disk access so that we can access files on disk. We're going to actually synchronize again with the other processors to make sure that they're started up. We're going to start the first user process. So this is that process ID number 1, which is traditionally named init. And the code to start that up is a function called user init here. And then every processor is going to call this MP main function, where we've actually booted, we're mostly initialized, and we need to do the work that we do at runtime. So that MP main function is here. We're going to print a message that says starting CPU. We can see that over here in our boot log. No, we can't. Let me boot up xv6 again real quick so that we can see that happen. So we can see that CPU 0, that would be the CPU we've been following, prints out starting CPU 0. And then this is a simulated dual core machine. And so we get that message printed out twice because both CPUs are going to run this MP main thing. And we can also see that init is starting up a shell, and there's our shell. Now what every processor is going to do is call this function called scheduler. And scheduler is the function that the kernel is going to spend sort of logically all of its time in. Not actually all of its time, but logically what we're always doing is sitting running the scheduler function. So let's go find that scheduler function. It lives over in a file called proc.c, and it's named scheduler. So the scheduler thing is an infinite loop right here. For semicolon semicolon means we have a loop that's going to run forever. We start off by enabling interrupts because they had been disabled previously. And then we're going to take a lock on the process table. And we're going to loop through the process table and find a process that it's marked as being runnable. Processes can be in a bunch of different states, but if a process is ready to actually execute, it'll be in the runnable state. When we find a process named runnable, we keep going. When we find one that is runnable, then we're going to do the rest of this. Then what we do is we're going to switch our user virtual memory so that we have the CR3 register set up correctly so that we're in the address space for that process. We're going to change the state from runnable to running. So we have one process running. We can have one running per processor. And then we're going to call this switch thing. And switch is not going to return immediately because this is going to do the context switch from executing this kernel code over to executing user code. So this is going to load registers and stuff off the stack and make it so that we are executing that user code. When that user code eventually gets interrupted or tries to do a system call that schedules it out and makes it so that it's no longer in the running state, we'll go ahead and switch to kernel virtual memory, and then loop back up again to find another runnable process. And logically, all the CPUs are doing this all the time. And that's sort of the whole story on the boot process for xv6. So let me go ahead and break here, and then we'll come back and look a little bit more at what else is in xv6, and probably more interestingly for the homework, how to implement a system call in xv6.